Welcome back. We're about to get into a section where we look at objects moving in circles, and so in case you haven't thought about that for a while, here's a review. So, objects moving in circles, you can make this happen by taking any object on a string and whirling it around your head, or you can have a car driving around a circular track, or a moon orbiting a planet, or a planet orbiting a sun. Those are a lot of the examples we do when we're first teaching this. And what's coming up in the next unit is we're going to take charged particles and throw them into a magnetic field, and you can get them to run in circles by doing that and kind of trap them that way. And then by taking measurements of the circles they make, you can learn some things about them. So we'll look at the formulae that govern circular motion and see if we can get ourselves comfortable with that. So, the formulae that govern circular motion are in the bottom left section of your data book. There's this VC equals 2 pi r over t, and the AC equals v squared over r, and 4 pi squared r over t squared. We'll look at each of those separately and see how those are used. When you remember when we were doing kinematics, we looked at the top 6 formulae in here and we said don't touch these yet, we'll get to them later. So let's get to them now. Whenever you have an object moving in a circle, you can measure the radius of the circle that they're in, and sometimes we call that the radius of curvature, or if it's a planet orbiting, we'll call it the orbital radius, but anyway, it's a radius. And there are a couple of ways that we can measure how fast you're going around a circle. R is the radius of the path. One way that you can measure your speed around a circle is just with a radar gun or something like that. You can measure your actual velocity in this direction. So you can do V, which is called the best term for it is the tangential velocity. And the reason they use that is that this arrow is at a tangent to the circle. It just barely touches the circle at one point. So tangential velocity, or sometimes they just call it the velocity. And the other way that you can measure how fast you're going around a circle is to give the time that it takes you to go around once. And we call that the period. If it's an orbit, we call it the orbital period. The period would be the time in seconds for you to make one trip around the circle. And we can combine those in a few ways to figure out stuff about the circular motion. The first formula they give us is if you're looking for your velocity around a circle, or circular velocity, you can work out 2 pi r divided by the period. Now, this is actually a formula we know very well. You remember in kinematics we had a formula that said your velocity is your distance divided by your time. The distance you're going in this case is all the way around the circle, meaning you're going around its circumference. And so the circumference of a circle is 2 pi r. And the time it takes to go around the circle, you could just use ordinary t, but they tend to use this capital T that means the period. So this is something you could have guessed anyway. It's how far did you go divided by how long did it take. So that gets you your velocity, the tangential velocity, in case you ever need to find it. Or if you knew the velocity, you could solve for either the radius or the period going around a circle. And the other formula, or it's kind of two, is for centripetal acceleration. Because if you're constantly going around a circle, there needs to be something pulling you in towards the center. There has to be some acceleration that keeps you turning the corner, so to speak. And you can calculate that by doing v squared divided by r. Some places use capital R, some places use lowercase r, it doesn't really matter. So the acceleration required to keep you going around a circle depends on how fast you're going and how tight is the circle. Small circles require more acceleration. It's harder to do a tight turn than it is to do a big gradual turn. So that's one way we can find centripetal acceleration. And the other one is 4 pi squared r over t squared. So I said there were two ways that you could calculate how fast you're going around a circle. There's an acceleration formula for each. This one is for if you know your tangential velocity, and this way is if your how fast is measured as a period. So you can use either one of these depending what information is available to you. And let me scoot these over and make a little more room. Sometimes when you're going around a circle, instead of acceleration, you want to know how much force is pulling you in towards the middle. We call that a centripetal force. And they're actually fairly easy to find. You know we have a formula, Newton's second law, that says anytime you want to know your force, it's how much mass do you have times what's your acceleration. So we can take either one of these as our acceleration and just put an m in front of it. Anytime you have an acceleration, just multiply by mass, and you get force out of that. So we can write m times v squared over r. Or, taking this thing, we can write m times 4 pi squared r over t squared. Either one of those gives you a formula for centripetal force, force pulling you in towards the middle. If you're doing a centripetal motion, the force on you has to be changing direction all the time. If you're here, your motion is this way, and the force on you has to be pulling you into the left so that you turn the corner. But an instant later, when you get to this position, now you're moving this way, and the force on you has to be pulling in towards the center again. And if you get to this position, you should be moving that way. It's always a tangent. And the force on you has to be always in towards the center, and so on like that. So sometimes they quiz you about this and ask you about the directions of these forces. Your velocity is always at a tangent. It's going just skimming off the edge of the circle. And your acceleration, or the force on you, either one, has to be directed in towards the center. So you have to have a force that changes direction all the time. A string can do this because a string is always exerting tension that pulls in towards the middle of the circle, or sorry, the middle of the string. So if you're holding a string here, the pull will always be inward. That can make something go in a circle. Gravity is excellent for this because if there's a planet here, its gravity will always be pulling in towards itself, so that's always going in the proper direction. And you'll see in a little while that magnetic forces can change direction like this, so they're always at right angles to your motion, and they're always pulling you in towards the center. So any of those things can get you running in a circle. And when you're going around a circle like this, technically your speed is not changing. If you're doing 60 kilometers an hour, then your speed here should be 60, 60, 60, 60. But your velocity is changing because velocity is a vector. And if we asked for your velocity here, you'd have to say it's 60 kilometers per hour north, 60 kilometers per hour, that looks like northwest, 60 kilometers per hour a little bit south of west, and 60 kilometers per hour a little bit west of south. So a kind of gotcha question they can give you is your speed constant going around a circle? The answer is yes. Is your velocity constant? No, it's not, because its direction is changing. So I'm going to stop this recording right about here, just leaving you with these formulae that are already on your sheet. And I'm going to start another one where I do some practice problems so you can see what these look like and how we get the information we need to make them work. They're really not too bad, but if you want to see some practice, go on to the next one.